welcome.
Well, welcome everybody.
Oh,
We have sound.
yes, we do.
We're okay? Okay.
Let's go.
Yeah. So, welcome to our talk. Let's get the introduction out of the way, and then we'll dive right in because we have a lot of content, even for 3 hours. So, I'm Alex from Boxel. I work at Calibra for a while, for 4 years, but I'm already 30 years kind of in this career. You see my gray hairs now. Mostly as a software engineer, a lot of Java in my career, but more recently I'm an architect, so I do less coding, but I still like to code. I'm also a really community person, so I'm a contributor to Apache Beam, was to Apache Airflow. I also have a part in the OpenTelemetry collector, the Google PubSub receiver and sender. And, well, that's it. So, Max.
Thank you, Alex. I'm Maximilien Ritter. I'm way younger than Alex. I have more or less 10 years of experience working with Linux and observability. I was taught as a software engineer, but I actually worked essentially at hosting providers and ISPs. So my field of work is way more infrastructure than code those days. And on my free time for community, I do some self-hosting, and I shepherd some project, for example, the Garage project, which is a geo-distributed S3 storage engine. And at Calibra, I work with Alex. I'm a staff production engineer in the SRE team. And people usually call me the Grafana guy. And for Calibra, Alex?
Yeah, so we both work at Calibra for a while now. Calibra is originally really a Belgian company, started with some founders here in Belgium some more than a decade ago. The founders, although, moved to the US. There's like a lot of, it's more kind of a global company now, so it has like lots of Fortune 500 companies, and we're really focusing on data governance. So data governance is something really big companies have. The problem about those things, they actually want to see what data do they have, what are schemas are there, what are the policies between all those schemas, the lineage, how is everything connected, and that's what our product is all about. So we're not going to dive into the product itself, but we will take some examples on how we use those things in production or how it affects our observability. So the agenda. So left part is before the break, right part is after the break. So we're going to dive into the history a bit. So will be Max part mostly. He has like way more experience in there. Then we actually go about the man and the machine is more about dashboarding and reporting and so on. And then we dive into the signals. So all the signals that are out there. This is a big theoretical block. So remember, if you saw the abstract, we are way more into the theoretical part than the practical part. For that, if you really want to do the practice, in the afternoon there's a workshop. So about OpenTelemetry, so please feel free to join the workshop. We'll have a small demo at the end, but it will be a very short one. After the break, so we'll dive into OpenTelemetry, what it is, the community around there, SDKs and all that, and then do the small demo. Voila. I'm going to give the clicker to you.
Thank you. So let's dive into the history. We're going to see first metrics. So if you think about it, metrics were always around. You can see them everywhere. I'm more of a sysadmin guy, so for me, metrics show up essentially when I open top or htop. But even if you bring up uptime, you will have a couple of metrics in here. We have like the amount of time the computer has been up. You're going to have a number of users. You're going to have a load average. Those are all numbers, but they are numbers that you get instantaneously. They don't tell you anything about the past. This is just what happens now. If you think about it, and if you go way back, metrics, as far as I remember, at least from my history, I started to experience them using early tools back then, which was, I looked it up, was released in 1999, when I was 3 years old, actually. So 5 years ago. And back then, the metrics were stored in circular buffers with a fixed interval. And those were automatically consolidated with a lower resolution. And all the graphs were actually images that were stored and generated, a bit like a plot diagram. Those are still used today. A couple of observability solutions still use those things. The only annoying issue is because everything is images, then of course it takes a lot of time to process on memory and like create all of those graphs, and it takes a lot of space to store them as well, while people might not even look at them. Now, if you fast forward a bit, near 2006, people started to realize that creating database locally and then having stuff stored locally in RD was not necessarily a good idea. And they started to centralize things a bit. And that's where we started to have things like Graphite that were backend, or database actually, time-series database, that were storing metrics. And then the collecting part was actually split to another service. So here, collectD and StateD were daemons that were used back in the time to either collect or broker metrics. And those were pushing metrics to Graphite. And Graphite was exposing an interface that you can actually see on the bottom left, very, very barebone, which is something that looks kind of like a Windows Explorer tree for your metrics. And then you could query it to plot the metrics live. So this was all in near 2006. This kind of evolved a bit with the advent of InfluxDB and Telegraph near 2013. I'm not going to go too much into that, because what happened after that is near 2012, Prometheus came around. And Prometheus was one at SoundCloud where they had an issue, which is that teams were needed to kind of like shepherd their own metrics. They didn't want a centralized system. And they didn't want either a push model. And we're going to talk about that later. But a push model comes with some limitation that you need to have a central sync. You have traffic incoming. It's hard to kind of like manage. So they adopted a pull model where the developers were exposing metrics from their applications. And then the observability solution would actually pull those metrics into the database. So that meant that there was not necessarily a central data collection, but every team could have their own server looking at their own applications. And then aside of that, they created a slice and dice query language that allows them to kind of like slice on the data with different aspects. We're going to see that later as well. The interesting piece about Prometheus as well is that it came with an associated alert manager. So for the first time, people realized that actually we need a complete system, including alerting, which was existing in other solutions, but not necessarily part of the project itself. It was usually a third-party solution that plugged into the metric layer and queried it. So if you think about it here, two changes. The push becomes a pull, and then we have a dashboarding tool and an alert manager that are separated from the actual database. Let's review a bit the metric protocols that we saw over time. Again, we're going to see a bit of that later. But here I put 3 examples. The first one is from Carbon. So it's actually very similar to things that were used in RD, and even if for people who know SNMP, the simple network metric protocol, where you have kind of one address which describes the metric, and then you have a value and a timestamp, and that's it. So for everything, you have a single path that you can use for address. And that evolved a bit with InfluxDB that had something called the LAN protocol. And those are all like kind of like text-based protocol, no? Like HTTP. So the LAN protocol was the name of metric, and then a couple of what InfluxDB called tag back then, which were actually metadata about the metric itself, and then a value and an epoch timestamp. And then the Prometheus exporter had yet another format that is effectively very similar to the InfluxDB one, but they call the tags label. So if you see here, the big difference between the 3 is that, if I bring that, yeah, this works. Yes, and I need to move the mouse here. Okay. Yeah. So if you can see here, this here has everything into the metric name actually. So the verb of the request and the return code of the request are both in the metric name. And if you look at it here, you actually have named tags for those things. So that's a big difference between those two. Now let's move to logs. For logs, the most important thing, I think, when you look at it back, is the log structure. Most of the time, if you look at software that used to be here for decades, the log structure is plain text. So the logs are simple, plain English sentences. And then sometimes they do include metrics. Like, for example, something will tell you that it took like 0048 seconds to do something. But that metric is embedded into the sentence itself. So it's not really something that you can leverage or extract or query or plot because it's in the logline itself. Now this evolved a bit, and people started to put some structure into their text, mostly in not a normalized manner. So people will just like add brackets, add a column, comma, and everything, and a portion of the logline would be English or a sentence, and then a portion of the logline would actually be something that is more akin to structured data. And some of them actually push that a bit further. Like if you think about web servers, for example, they have very predefined formats for logging, and you can then I can actually like output a structured string that you can expect the format to be something. Like there's no sentence in here, there's no unpredictable content, everything is where it should be. But the line itself is still a plain string when you think about it. I put the last one a bit as a joke, but it's actually a real issue sometimes. Some of the logs are simply plain ASCII. So they're meant for humans. They're absolutely not meant for computers. And they can actually cause some issues if you just pipe them into central logging systems, because the logging system processes them line by line. It doesn't understand that the entire thing is actually like a log line. It's a single log line or a single view that spans multiple lines. Now, fast forwarding a bit, in recent time, we use JSON for everything, and so people started to use that for logging as well. And although JSON is a bit unreadable for humans, it is very good for computers because it is very unambiguous about the fields and the metadata that are in the logs. So if you look at this example here, you can see that you have a timestamp, you have a level, you have a logger, you have a couple of metadata about that particular log line. You have and you have various type of data, right? Like you have on the right, sometimes those are strings, sometimes those are numbers, and you still have issues because, for example, the timestamp, like it's not necessarily normalized, could be something else, could be like a format that you don't expect. So it's not like you can deserialize that record directly, but there's already a lot of progress, right? Like you need to guess where the fields are, they are labeled, they are separated properly, you don't need to worry about escaping things. And if you think about it, this is not really readable for a human, although you can still include the message part here, this one here, you can still include something that's friendly to a human. And then you can just tell to a human, hey, like just look at that and just disregard the rest. You can still get to it if you want. But if you just want to go through the logs very quickly, then you can just look at that message that is kind of like summarizing a bit the rest of the data. So I put together a bit of a log format scale between the humans and the machines. So the humans are on the left here, and then the machines are on the right. And if you go from left to right, you can see ASCII art, which is 100% made for humans. Machines don't understand it. There's plain sentences, which are very much geared toward human. And then you have formatted key value pairs, or partial, like what you see in the HTTP logs of a web server. Those are formatted on a specific format. And then JSON format, and then I put on the right, which is kind of interesting if you think about it, that some systems actually do record logs in a format that's not even readable by humans. It's usually binary. Think about a database system. The write-ahead log is actually a log, but it's just completely binary and not unreadable by any humans. So for the backends, just as an introduction to what we're going to see later, there's three kind of backends. There's the flat file backends, like a syslog, like you just get some content and just put it on the file. There's some columnar storage, like logkey or ClickHouse, which are mostly unstructured data. You just put them in here. If you have some indices, but if you need to do a search, you can just brute force it. And then you have some index storage. Elasticsearch is maybe the main one. Graylog is built on top of Elasticsearch or OpenSearch. No. So those have various level of flexibility as far as querying is concerned, but they also have various costs in terms of how much processing it takes to store the data and then to take it out. Let's move to traces. I think those are maybe the less known of all of the free signals that we're going to be presenting here. I just put this because I found it funny. When you think about it, we already have traces in the form of stack traces. Stack traces are, especially in Java, something that you often encounter in a system, and they will give you information about a single service, because this is just your code in your program, this is just function calls, it doesn't necessarily give you information about any slowness, because this is just an exception. It doesn't give you any timing. And then there's no metadata in it outside of the parameters of, well, not the parameters, but the prototypes of the functions of a method and the stack trace itself. And if you think about it as well, sometimes there's way too much data. I can give you more reasons, but big stack traces are one of the issues that we have at Colibra. They can get so big that they can even cause problem in the logs themselves. So better than stack traces, we can do traces. And traces have some requirements, right? So what we want to see is the errors, like we do in the stack traces, but we also want to track latency. If something is slow, even if it succeeds, we want to see where it is slow. We want to do that across services. So if we go from one service to the other, we want the data to be stitched together so we can piece together the journey. And then the last one is we want to provide context. So if there is anything interesting about a particular request, like, I don't know, the HTTP verb, or potentially some information about the user doing the request, we want that context to be associated with the trace itself. All of that kind of like gears toward or points toward the fact that traces do require deep code integration, because most of those information are things that are only available in your actual code base. So compared to the other things that are still outside of the applications, tracing requires like even more integration into your code base, even within your actual methods or within your actual business logic. I put together a little row of all of the protocol over times. There has been a couple. So tracing originated, I mean, in its current form, originated somewhere inside of Google around 2010. Which means that it's compared to the metrics and the that we saw were from 1999 and the logs that even predates that, it's a relatively recent signal. It was popularized after Twitter open sourced Zipkin in 2012. And then after that, there was a couple iterations, Jaeger at Uber, and then Open Tracing. Open Tracing came around because people were not happy, especially Yuri Shuko, who put the Mastering Distributed Traces book at that time, was not very happy with the state of the industry. So Open Tracing was already a leap forward compared to the other protocols. And then even after Open Tracing, Google came back again with Open Census, that's kind of an open version of the census tracing that we're using internally. And then all of that cascaded to 2019, when the W3C normalized some of the tracing context, and then OpenTelemetry picked that up and kind of joined the Open Census and the Open Tracing project under a single umbrella. So if you think about it, I put the standard exclusivity here, because in such a short period of time, we still had like 5 or 6 iterations, maybe 3 if you count the open source one, of the tracing protocol. I also put Kubernetes in here because it's interesting to see that Kubernetes came around right around the time where tracing became much more prevalent in the public space, as basically we started to do microservices and then have more and more application that required tracing simply to understand where requests were going. And I'm going to pass it to Alex for Man of the Machine. Oh, no, sorry, that's my part still. I forgot about the dashboarding. So let's now talk about a bit about the man and the machines, because we talked about the history of all of the signals, but this is all meant to be consumed by humans, right? Like computers do consume a bit of alerting, but there is a lot of things that are consumed directly by human, and dashboards are one of them. I put here an example of a Prometheus dashboard. That's actually, I think, the default node explorer dashboard. And dashboards are essentially something that you consume to get our attention drawn to something, right? Like you want to have an image, and then something in that image is going to draw your attention. Here, for example, this is actually from a production system, not at Colibra, but elsewhere. You can see that there is 2 things that are interesting. One of them is that the load was kind of high, and it's less high now. But the load 5 and the load 15 are kind of high, which points to some kind of CPU or I/O issue. And then you can see that the root file system is actually 97.4% used, which is likely not a good idea. So dashboard points those things to you directly. They basically expose information to you, and a good dashboard will allow you to directly see if something is wrong or not. Although that is usually the case, mastering dashboard is difficult because showing that information in a way that is consumable by human is difficult. Dashboarding tools are limited. You can not always do what you want. The amount of type of graph that you can do depends on the tool that you're using. The query languages are limited as well. So the amount of data that you can query or the kind of transformation that you can do are not always the one that you want. And the human perception is limited. If you end up with something like this, like a human will not get any information out of it. Like this is something that we're just going to see and say, okay, there's no information that I can get out of this. And this is, again, like something taken from a real dashboard. So the two things that I wanted to stress out here is that for dashboards, you need to plan them. You need to think about what you're going to show. You need to think about what's important. And you need to remove anything that you don't use. Because anything that you don't use is just going to be noise for the user and is going to distract them from what they actually should see. Which doesn't mean that you necessarily don't have to not show everything. But if you do it in different dashboard. Have a simple dashboard that people can use, and then have maybe a more drilled down dashboard that they can leverage if they need to go further. So this is an example of a kind of a simple dashboard. This is for a UPS, so a power supply with a battery for a computer, and you can see that this is very straightforward. Again, this is a bit of a best case scenario because there's not that much data to show, but still, you can see here very clearly that you have a charge. You can have a running time that you can have remaining. So here 20 minutes. You're going to have a state of a power supply. Is it online or is it in battery? And again, you have that state here reiterated. And you can see here the plot of a battery charge and the load value, so how much of a load we're consuming right now. Reporting. Alex, do this one.
Yeah. Just one thing on dashboarding though. You see that development teams, the first thing if you ask them about observability is like, how can we build dashboards? And that's a good thing because then it actually forces people to think on what do I need? Because of course you start with the CPU and the memory and so on and so on. And you get those things almost for free. But then, okay, but that's not the whole story. Yeah? And so it's actually a conversation starter. For us at Calibra, we actually ask teams to do that, but they quickly come to kind of your team to say, help us. So because they're kind of the expert on observability, and it's the first actually interaction between Max's team and all the development teams within our company. So next thing, error reporting. It's kind of a thing that you actually distill from logs, like you saw those stack traces that were already touched upon. Error reporting, some tools, you get them kind of out of the box for free, but you quickly end up with dashboards like this that goes from pages into pages and pages of like stack traces, and they're unusable. So I'm going to be honest, at Calibra we are at the same place. We can't use those error reporting because you should actually think about those things from day one. If you have already 2 pages of error reporting, is almost impossible to catch up because there will always pop up new ones. You could. It's like your zero email inbox. You should get like 0 things in error reporting unless there's really something wrong. If something pops up, you should tackle those immediately and get them resolved. Because remember, if in your code there's kind of a stack trace and you handle them, don't put those stack traces on your logs. You've handled them, so you know what to do with it. You're handling them, you're returning an error code, or create kind of something else with that, and just don't put them in the logs. And then you get like nice empty error reports. That is like your 0 email inbox.
And with that empty error report, you can do alerting on it. So let's talk a bit about alerting and notifications. I have somewhat of a strong opinion on it, being someone that had a hold the pager for quite a while. I do feel that an alert must not fire unless there is an issue. And this is not negotiable. If you do a plan change, if you do maintenance, if you deprovision something, the alert must not fire. And the more an alert fire for something that's not actually an alert, the more you exhaust your alert team, and after a while, nobody will pay attention to them. So an alert should always indicate an actual problem. And some people have a tendency to alert on symptoms. Symptoms are not necessarily problems. If you think about it, if your backend is running at 70% CPU usage, that is not an actual problem unless it actually impacts the service, and it doesn't necessarily do. So unless the latency goes up, unless you have errors at your front end, or unless there's any kind of processing issues, 70% CPU is actually a good target because it saves you money. So an alert should always indicate the actual problem and should not be some kind of like vague signal that might or might not indicate something is wrong. That doesn't mean that those signals are completely worthless, though. It means that they're not necessarily worth waking someone up for. And in the verbiage that we have internally at Collibra, we call them notification or report, meaning that we still kind of like keep a log of them. We just like don't notify actively someone about them. But they are very useful because if something goes wrong, then you can go to the notification report and then you can actually see what has been happening, what are the noteworthy signals that were happening in the past while, which can help you greatly with your investigation. One other thing is the alert conditions. So this is, I couldn't find a better example, so we're just going to look at disks, because disks often fill up, and that's, I think, an issue that everybody has. So if you think about it for a disk, people usually alert on the disk being somewhat up, like if it's filled up at 80%. And then they have some kind of either manual or automatic process to resize it. But that's not necessarily enough, because if you have very small disks, and I'm thinking about PVCs, for example, on Kubernetes, which are often very small, 80% is not that much. Like if you have a disk that is 10 gigabyte, then that's only 2 gigabyte, and by the time you get to resize that disk, then maybe it's going to be full. So one of the things that you could do is say, hey, I want my disk to be at least 80%, like at least 20% free, and then have at least 25 gigabyte of storage on it. So even if it's small, then I can kind of make sure that I have enough buffer for it. So that's already two conditions. And then when you think about it, and if you learn a bit about file systems, then you learn that actually most file systems have a limit of how many files they can store on the disk. And that means that you need to alert on that as well, because you could technically have space on the disk, but not necessarily be able to write a file on disk. And so you add another condition to your alert, which is the number of inodes that is used on the disk, and you want that to be below a certain value. So that's already three conditions, right? And after that, we need to think about the time window. How often are you going to check for that alert? And this is important because things can happen in between two runs of an alert. And if your alert is a goat, something that Alex is going to talk about later, then that's even more important, because what happens in between the two runs you will not see. So if you think about it, at time t, you have a disk that's 75% full, so it's not alerting. Your application, so you check it, and the alert says, no alert, it's 75. Your application is write to disk 10 seconds later. It writes for 30 seconds, the file is too big, it basically fills up the disk, the application realizes that it cannot write that file, and it deletes it. It just deletes the temporary file. You're back to 75%, your alert came on, and the alert says 75%, no need to worry. So you really need to think about the space, like the period at which you're alerting, because otherwise you might miss some things.
But Max, why do you always refer to disks? We're writing microservices, right? Why do we have disks?
We have this because people still store things, even for databases. So talking about microservices, you often have dependencies, right? Like a service A depends on a service B. And you have a front end, you have a back end, you have a back end, and then you have another back end that depends on it. Service B is down. Who should alert? Service A cannot process requests because it depends on service B. But what are we going to do? Are we going to alert for service A, service B, maybe both of them? Most people will actually say both of them, because I mean, there is only 2 services. You likely just want to bring attention that the 2 of them are affected. Now, this changes a bit when you start to have multiple instances of them. Let's say I have 1,000 instances of service A, and then I have a couple of instances of service B. Service B is down. What do I want in the alerting? Well, if we still say both, then we have 1,001 alert, which is a lot of alert and not necessarily something that will allow us to see that actually the root cause is service B being down, not service A. So those things are, those things are not necessarily straightforward, and you need to consider them when you build your alerting to make sure that when you alert, you actually point toward the things that are broken. Now, more conditions. The client cannot reach the service A. So you have a backend service, and then you have a client, like let's say an HTTP client, that tries to reach out that service. Up until now, we were considering that the service was actually logging some state. So if something is wrong, if the service is down, then you can see it in the service itself. But let's say you have an issue with the client. The client cannot reach the server for whatever reason. You have an issue with the DNS record, or your load balancer is down, or something like that. Then the service A, from his perspective, everything is fine. It's just not receiving any request. So how do we alert on that? So the answer usually for that is to have some kind of client monitoring. So what you call black box monitoring. So you can have a probe somewhere that will actually probe the system from the outside and then give you some kind of external visibility. So now you have 2 pieces of information. You have the actual client that you're simulating, and then you have a backend itself that is going to tell you what it's doing. And then another case, which is a bit more interesting, because it happens quite a while actually at Colibra, especially when we start to introduce SLO, is that we start to look at HTTP response for issues, right? So we say, hey, like, if we receive a certain amount of some kind of response, then that might be an issue. The issue here is that the semantics are not necessarily on our side. If I get a lot of 400 or 400, like for any kind of 400 or 3 or 404, if I aggregate them together and if I compare them to the rest of the traffic, I can actually see trends. And if, let's say, if I have 99% of them, then I might think that actually this is an issue with my service. And what turns out is that often those can be caused by bad clients, people hammering the service and they got the credentials wrong, or just someone that just a random bot passing by that just like hitting a page that doesn't exist anymore, and then you have a lot of 404s. So the takeaway from that is that if you want to do those kind of thing to kind of like analyze the health of your service, then often you actually need to have a composite of the client side to see if the service is actually performing what it needs from the client perspective. And then you need to have something on the backend side as well to make sure that your service is logging the thing that are expected and the thing that are just noise you can just discard. So if here, for example, if it's just a lot of 404s and you know your service is not necessarily impacted by any of that, you can just discard those because you know that they are not an issue. Same thing with bad credentials. If someone is hitting you with a bad user and bad password, then maybe you can discard that. But if they hit you with something which is like wrong credentials, but something that's wrong with your backend, actually you perform, let's say, authentication on a separate service, then you might need to actually log that as an error. But if they messed up the credentials, then maybe that's not your problem. Interesting. I just got the okay. There's a bit of lag in the display. So a bit of a recap, some answers. I'm not going to go through everything, but basically, black box monitoring is something that you likely want to do. Implement alerts when the traffic go below a certain value can be also be interesting. If you expect a consistent amount of traffic, then having no traffic at all could be a very good indicator that something is wrong. And then, by all means, please, when you implement alerts, make sure that they are deployed and removed with the workload that they are on. Although, caveat to that, it happens to us one time, make sure that you have some manual alerts as well, because if something very, very bad happens, and then the entirety of your service gets descheduled, then you might actually deschedule the service and the alerting with it. So just make sure that you have some kind of like blanket alerting to make sure for the things that are like modified once a year or something. And then if you cannot trust alert, move them to reports. And after Alex for signals.
Yeah, so actually continuation on this, we actually on our dry run, we saw that we forgot to talk about SLOs.
Oh, yeah.
That is very much near to reporting, because alerts, they're pretty complex, and let's be honest, we haven't cracked the nut for ourselves as well at Calibra. We even have like our own yet another alert handler to actually do those things, do those complex composite alert conditions. It's complex, but actually something that's maybe easier to introduce to teams is SLOs and SLIs. It's still kind of recent. Not everybody's using this, and also in our company it took a while to actually get some backing to start to introduce that, but we already saw working with one team that actually pays off. And this kind of more in the reporting space, because SLI is service level indicator, and as SLO stands for service level objective. So you actually go, and it's more to the project manager that they actually talk to, is like, what's your objective of your service? And the first thing you notice is like, I don't know. So you have to help them a bit. It's like, how critical is your component? Does it have to have 4 nines or 5 nines or 3 nines or something like that? Like 4 nines, we should have looked it up, but like it's like in the minutes of downtime per year or something like that. So it's a conversation starter. So you ask the teams, what do you expect? And you help them a bit, and you go to them, okay, this is my objective. And then you start working on an indicator. How do you measure this? There are several ways to measure that. And the how is not important, but you get then the number of an indicator and how close is this towards your objective. If your indication says that you're below your objective, what you then do is like you burn an error budget, and that actually is like a pile of money compared to a pile of money. And if you say like, I'm behaving bad, you actually always pay off the debt from the error budget. But you have a pile of money, so you could say like, well, I have money for this amount of errors. But if your money is gone, it actually says like, okay, we're behaving badly, and it could help the project owner to say, we have a problem with our system. We don't see it like in user behavior, although lots of your objectives should be focused to users, but like it's only a small percentage, but it's bad enough that we should work on this, and it could give the team an incentive. It's like, okay, let's get better and go and work on this, so our indicator is back above our objective.
One more thing that's interesting about SLO that we noticed is that often when we go to team to ask them about what they want for their SLO, we also ask them what is the expected behavior of their service, and what do we consider as a good event, and what is all the rest. And often we notice that the teams don't even have a proper definition of what is actually expected of our service as a good behavior. And having that discussion for the SLO actually drive around the fact that, hey, like, what do you expect? Like, if your service starts to return 404, is that an issue or not? And it kind of like, often initially they have a very reduced definition of what they want as a good event. And as time goes on, they actually discover more and more things that they did not expect and that we add to the definition. So they say, hey, this is actually a problem, or hey, this is actually fine. And then they built into their service observability to be able to tell apart, like if they are returning 403s, are those bad authentication, or is this the backend failing to authenticate the user because we have some kind of issue processing that on our side.
That's really the example that we had from the IAM team, where we implemented a get token, right? Yeah. So the normal behavior is like 400 and 500 is bad behavior. And actually we saw on one of our clusters actually the budget being burned like in minutes. But that was because there was a client that was unauthenticated, it was not good credentials, and then we came back, it's like, that unauthenticated, maybe we shouldn't put that part of SLO, but actually remove that, but not remove it blindly. Maybe we need an error for that to actually go and talk to that client team is, hey, you have a bad behavior, we need to have an alert on that. So voila, on this, the signals. So we have actually several systems, and we're gonna start with actually the biggest block, and actually my least favorite part is metric. But why do we start with that? It's actually important because it's all about aggregation. Even the later systems, signals that we have, eventually, if you want to build an alert or have something in a report, it actually is a number. And actually, well, that number is actually a metric. But here is from the point of view of your application generating directly metrics. So, but always keep in mind a metric is always an aggregate. So you lose information. So let's start with a gauge. So a gauge, where can you compare it with? It's like the best thing you can actually compare with is in your car. Your speed meter is like, it goes up and down if you drive too fast. It is like way above 200 or something like that. And if you drive normally at 50, then you're okay. Or a pressure meter or something like that. So that's a gauge. So mostly, generally, it goes up and down and up and down. Here I have an example of a CPU that goes up and down. So, oh, yeah, thanks. So here I have an example of the CPU where you actually make a gauge. But always remember, if you're doing something in an application and you're measuring something, you're actually not doing it constantly. You're actually taking snapshots at specific intervals, and then you're measuring. The downside of a gauge is that, like shown in the bubble here, is like if you have some peaks in the middle and the sampling precision is not high enough, then you actually miss them. If you look at it like that, so your sampling interval are the orange dots, and if you look at the graph, it's actually you don't see those peaks. Sometimes it doesn't matter, but sometimes you want to really know that you have those peaks in between your sampling intervals. The next type, the next metric type, maybe good examples of this, of a gauge, is like a pool. Instead of CPU is something that really goes sometimes very fast up and down and peaks. You have peaks like that. But good examples of gauges are pools, database pools, where you actually have a specific limit. Let's say you have only 50 database connections. You want to actually monitor that pool, and it stays well below 50. If that's kind of lock, okay, you can have all those bumps that you don't see. But sometimes if you have if it's nearing that limit, sometimes it locks itself and it will stay there for a while in that 50 range. So that's actually a good example of a gauge. This is kind of my semi-favorite. I prefer more to have counters. So actually, how many tokens did you provision? At the moment, a mistake sometimes if you don't know the difference between the gauge and a counter is people sometimes go directly to gauges. And like if you count something, if you put like a gauge that always go up and up and up, then you have problems. So that's why we have counters. So again, if you have the analogy with the speed meter, it's like the odometer. It's like what distance did I travel? It is actually a result of how fast that you drove. So if you drive a lot, that counter goes up more quickly. So the thing is, a counter always goes up. So so you actually compare to this. You have those intervals, and then you really see that the counter goes up. A thing to notice, though, because you're actually counting something, is that that metric is produced by your application. So at the start of your application, that counter is 0. But in the life cycle of your application, you will have upgrades, you have a new version of your application, or if you're working on Kubernetes, rescheduling of your application, it goes down, it pops up somewhere else. You actually have multiple versions of applications. There are restarts. So if that counter goes up, if you restart, the next version of your application doesn't know what the previous version was, because yeah, it's all in that application. So you have a restart on this. This is what I want to show you here in this. So you always restart your counter. That's kind of a problem. Some of the backends support this, but how can we do better, actually? So another version of counters are delta metrics, or delta counters. Is actually, I have a specific interval where I measure the number of clicks that I have. So that means that like every minute or every 30 seconds or whatever, I actually click, click, click. Okay, I had 5. Okay, click, click, I only had 2. Click, click, I only had 3. And that's, you can actually go from the previous one, from here, directly to this, and you have actually the same information. The only thing is you only have, you only have the numbers. Always like a very low number of counts. It's actually, if you have your backend supports this, is actually way better. It does also, though, have another downside, though, is what happens when there's kind of a glitch into when you take your sampling, and some measurements are not made, you actually lose that. It is a downside. If you have an up-down counter, your application didn't restart, within an interval that you were not measuring, or there was a glitch in your system, you actually catch up. Like 3 minutes later, okay, in that 3 minutes we have so many number of clicks, but here when there's a glitch, you actually really lose that data. But if you have like a lot of data, that shouldn't be an issue, because like it's the power of a lot of numbers. You always have to take into account that you have a margin of error. Maybe you can actually go from a counter to from a gauge to a counter, because like the counter we see that's a bit better because you have a bit more precision. Taking the CPU example like we started with, you actually can do that. CPU, if you take the speed bumps and actually look at CPU time instead of like the core cycles consumed, you really can do better. So instead of like this, you actually measure the number of cycles, microcycles that have been taken, measure them, and here you see in the peak, you actually see how many CPU cycles you burned. You flatten them, and then actually scale it up, and you actually see your peak is actually back, because you actually took another approach of measuring something. So it is good to actually look at, I have a gauge, that's the first thing that comes to mind, but can I measure it differently? And then you actually can use this trick of a counter and actually have a better graph and better data. Next, histograms. So those previous types, in generally, they are taken in a fixed number of intervals. But let's say you have a system that produces like different measurements on different times. For example, an HTTP request, you actually want to measure every HTTP request that comes in. For example, what is the size? What is the duration it took? Or what is the size that that request took? And then it's very hard to actually go to a gauge or a counter. You can have a counter, but you're just adding and adding stuff and losing a lot of data. So then actually histograms are a better approach. So here the example, we have like the HTTP requests spread around. They're kind of scattered around, not in a fixed interval. So if you make an histogram about that, you actually just count them, you bucketize them. You say, oh, I'm interested in a bucket from 0 to 1, 1 to 3, 3 to 10. And you actually measure when those things are in those buckets. And then you actually have a histogram. You all compute that in your process, and you send it out to your back system. Histograms, in generally, I think Prometheus, I don't know if Prometheus was the first one to introduce this. Maybe there were a few other ones.
I think there were in OpenTelemetry.
Yeah, but Prometheus
Prometheus
actually used them. But they used a classical approach where you were in control of the bucketizing. You said like your process said like these are the buckets that I'm interested in with. More pushed from OpenTelemetry, and actually Google at the distributions as well. So that you probably saw. The thing is, we want to have like a way more mathematical approach to this, and so then comes the introduction of exponential histograms. So it's actually you have two numbers. It's like a base and a scale, and with those two numbers, you say how precise do you want to make my measurements. So I've had here a spreadsheet to actually show each base and each scale, how you get like the precision. You see, the higher the scale is, the more actually buckets you have between like the normal numbers. So just like normal histograms. Maybe it was worth to go over this example. It's very familiar. I want to go through kind of an animation, but it has some explanation. Normal exponential histograms already have some of those measurements built in. They're part of the data structure. So the count is, of course, all the data that's in there. The number of samples that you took, and the average. Actually, the average is not part of it because it's just the count divided by the number of samples. I want to show though that histogram has a cost, so it has like a number of bytes. But if you don't have like lots of data points, then it's not worth it. But if you have lots of data, you will see that the histogram size will actually stop growing, while your bytes of your raw data will grow. So again, it's a way of aggregating data, but you can keep way more information in there. So, I'm already counting, sorry. So like an histogram, you build up your histogram with more and more data. You see that the histogram is still growing, because as soon as you have like a dot larger than the buckets that you have, it will grow because it's bucketizing. But after a while, it will get more interesting. But way too much time in this. So, but here it's going to getting interesting in an exponential histogram. If you normally have like averages or something like that, if you have outliers with your normal gauges and so on, in a histogram you can capture this. So I've added a number completely to the right. If you just have like a count and the number of samples and do that, your average actually bumped a bit to the right, but not a lot. But because you have those things in a bucket, you actually capture that data. If that goes to your backend and you can display it, it could really help to troubleshoot. And certainly if you add exemplars we'll see when we go traces, it's kind of a point in time where you say, this is a trace that produced this number. And then you can troubleshoot. Those outliers in general you call tail latency, if it's about time. And that's what you're interested in. what is producing those things? What is the reason for this? Because it's maybe not the place where you took the measurements, but maybe something that was calling and that was producing that slowness. And you just wanted to see that the raw data is growing, but your histogram is actually smaller. Okay, next. Characteristics, back to you.
Thank you. Okay, so let's look a bit at, previously in the history, we saw some format for logs. Here, I want to bring your attention a bit to the format for metrics. So, as I said previously, there is a bit of a choice of vocabulary that happened in the last few years. I think InfluxDB used to call the metadata tags, and then Prometheus came around and they used to call that labels, and then now OpenTelemetry call that attributes. In the interest of saving the body some madness, I'm going to call everything that is metadata an attribute now, because that's what OpenTelemetry calls them. So if you think about it, you have now for metrics, not necessarily formatted like that, but this is just kind of like an example format. You're going to have a series name, and then you're going to have one or several attributes, and then you're going to have a value, a single value. Now, what I'm going to talk about here is cardinality. And cardinality is important because it's going to influence the performance of your metric backend and what you can do actually. Within like the realm of like possible things, and it's very similar to complexity in algorithms if you think about it, like big annotations and everything, but applied to your metric backend. Here I'm taking the example of something that is actually a metric with an attribute that is the HTTP code, and I went to Wikipedia. And I copied dutifully all of HTTP code that existed. I might have missed some, but you can see here, for example, that the teapot is here. It's here, 418. This effectively gives us a theoretical cardinality of 64. So potentially, if you have an attribute that is an HTTP code, and if your application doesn't use made-up HTTP codes, then this should be one of those 64 values. Now, cardinality combines in the same way that your complexity in your algorithm combines, right? So here, if you have the HTTP code and the HTTP verb, then same thing, the verb can have different values. And again, I went to Wikipedia and I dutifully copied them and forgot some even. I think you never heard of link and unlink because they were actually never implemented, as far as I know. But the others should be pretty familiar. Head, get, post, patch, option, and delete. And with link and unlink, that gives us a total of quote-unquote standard attributes for the verb, and there's 9 of them. So if you combine them to the 64 code that we got before, that gives us 576 possibilities. No, not necessarily all codes are valid for all verbs, but that's the kind of like theoretical maximum that we're looking at. Of course, this is all in theory, and practice is a bit different. And because we are very practical people, and we live in production with practical things, we can forego some of those things. We're not researchers. We know that we're only going to see some HTTP codes. I actually forgot patch here. But the codes that you're going to get the most are going to be head, get, post, put, and delete, maybe patch, but not necessarily all of the others. And for the rest, I actually took a sample of what we have at Colibra. So this is a 15-minute sample of what we saw passing. And then you can see that there is not that many of them, right? Like on the codes, we only have 23 of them. You can actually see here, there's a 299 that is a made-up code that Envoy uses for Istio. But in practice, we see that if we multiply 5 by 23, that's give us more or less 100, and that's way less. That's like a quarter of the value that we had previously. So simply by moving from theory to practical, we already divided or estimate by 4. No, the reason why cardinality is so important is because it kind of governs how you're going to create your data, right? The amount of metadata that you're going to be able to put in here, as well as the difference that you can have and how they combine is what threatens you. And most metric systems will warn you about cardinality explosion simply because they are going to hold those attributes in memory for indices. And so the more you have, the more memory the backend is going to consume. Some backends have some kind of like soft limit. Some of them don't have any explicitly. For Prometheus and for all good measures, because you don't necessarily know which backend your metric is going to be sent to, we would advise to keep your cardinality below 10,000 per metric. To give you an idea, a normal Prometheus system, like a single instance, can handle approximately 10 million in terms of cardinality across all of the metrics. So this number is quite low compared to what you could get. But it can go pretty fast. Like, let's say you start with the verbs and everything, and then you start to add like API endpoints, and then suddenly you can want to put a user ID in here. Putting variable IDs in your metric as attributes is something that you can do, but you need to do it cautiously because that attribute is going to be iterated upon. And if it's a user ID, maybe that's fine because you have like 10,000 users, and so that the space is bound to the amount of users that you have. But if you go in here and start to put sessions ID or job IDs in here, and those are just generated and they just like keep coming and coming in different shape, then you don't necessarily have a limit to how much you can have, and that's where redundancies lie effectively, because you're going to have an unbounded value that's going to combine to the rest, and then that can quickly blow your backend. So for the sake of your query performance and also for the sake of your wallet, try to keep the cardinality relatively low, monitor your usage to make sure that it doesn't blow up, make sure to drop the metrics or the dimensions that you don't need, and at the same time, drop the one that you don't use. If you're not using something, if you never use something, maybe you can just drop it and enable it only if you actually need it. So you can configure your software to actually log metrics, or not log metrics, but produce metrics with variable level of cardinality. Maybe if you don't need to do something per user, like for example, the number of calls, if you don't need it per user, maybe you can just have that as a global counter and only enable it for users when you actually need it. You can configure that in the software, but as Alex will explain later, you can actually do that in pipelines later on. It's just much more simpler to do it at the software layer. Yeah.
I'm just going to do the same thing again. Just to go back again on cardinality. I just remember one of the things that we actually, because it was talking about users, one of the things we first dropped was the HTTP calls that in the beginning there was kind of the application, kind of our monolith that actually did track all the REST calls and actually did it per user. Yeah. And those are the things that we actually dropped because it was killing our backend, because not only is that per user, but we have kind of thousands of instances for our different customers. Because we have a SaaS platform, people come and buy our product, we host them for them, and those measurements were then even times thousands, and our backend also had a problem.
And most of them never changed, right? Yeah. Like a user would come by, and then the application would create a metric for it, and then that user would go, but the way that controls are created in most backends is that they just persist forever. So as effectively every time a user would visit, you would add one more metric that you would gather every time, and that would just add up to very big amounts. So we ended up just like dropping all those metrics altogether simply because first, no one was using them really outside of very specific use case. And the second one is that indeed, like there was no practical use of that, like compared to the amount of money that it was costing us. This was also for the rate limit for token buckets. Yeah.
But not only the backend, because it's also your client also keeps that counter till your process is restarted. Every time a user actually is entered on the system, it starts a counter for that user. If that user doesn't come back anymore, actually your backend is constantly producing, I had 5 calls for that user from a week ago. I had 5 calls from that user a week ago, every minute, like on a continuous basis, till the system has been restarted. And certainly that was on our monolith. That was we have way more microservices now, but that monolith was actually only restarted once a month. So it was producing lots and lots and lots of data at the client side as well. So not only the backends are struggling, but also the clients actually takes a lot of memory in producing that. And if you look at Prometheus, it has like a slash metrics where you produce those metrics. It could be very hard actually to open that, and sometimes it times out.
Yeah, like you would have like metric endpoint with like megabytes of metrics literally, and then you have a lot of issues because then your scrapers have to scrape thousands of things which are like actually couples of megabytes. Like we start to move actually to gigabyte of data every 30 seconds or every 15 seconds, and all of the transporting all of those metrics is not free either. So the more you have, and the more you pay for transport, the more you pay for storage. In everything metrics, less is more. Like the less metrics you have, then the more you can afford to keep them for longer, and the easier it is to just kind of like look around them.
So actually another characteristic is like how do you get your metrics, whatever type they are, out of your process. So we see actually two kind of ways to get it out. One is push, and the other one is pulling. In the beginning, like you said, in history, actually push was more more common. And then with Prometheus, actually the pull model kind of got more popular. Certainly with the focus on each team running their own Prometheus instance, and it was just scraping local data. And also the nice thing about that is because it's exposed as a slash metrics in generally, it's very easy to debug. So that's actually the most popular way of producing data, but actually like everything in history and certainly in IT, everything comes back. We actually see that push is coming back, and that thanks to OpenTelemetry. We'll see later on OpenTelemetry is really kind of a push-based model, although it can handle everything. Their native format is really make your application responsible of pushing the data out. So I predict that with this and a decade, we're back on push again due to OpenTelemetry getting more and more popular.
Push has a lot of advantages. There's some drawbacks. One of them, for example, that we really don't like on the infrastructure team is that the sampling of the data is governed by the person that pushes, right? Like they push data and you accept it, and if you decide to push something every second, there's not really a lot that you can do. Or you can do, but at grades, you need to manage a state and then kind of like drop one metric out of 5 or do some kind of sampling. Pull is a bit different because they just expose the data and then you just come get it whenever you want. But that also means that you need to get everything, right? Like if they created something at some point, then you need to pick it up. In our case, we do a bit of both right now at Colibra. Some new services are push only, which helps a lot, especially for things that are short-lived, like jobs that runs for 10 seconds, and then the discovery infrastructure doesn't have time to pick up the endpoint and then to discover the metrics. So pushing metrics actually helps. And then for more systems, otherwise, we still rely on the pull model, but then we pull with an agent that is closer to the system. And then that agent is actually going to push the data to the backend.
Yeah, certainly when we started with OpenTelemetry, we were very early adapters, and we were starting with trace and slowly adapting the other formats. We had a standard on something, so we standardized on Prometheus. Now we leave it up to the teams to actually pick or OpenTelemetry push or Prometheus pull model. So
do you want to talk?
Yes. So the next thing actually push. When you have push, of course, then where do we send data to? So if you look at documentation, the thing is like, okay, here's your backend. Just configure your backend and just push towards that backend as not an intermediate step. And that works, certainly for demos. But because we're going to do that in the demo as well. But remember that actually not all backends can handle the amount of bursts of data sometimes that you are producing. So maybe you need to think about kind of queuing those systems. We'll go deeper in that system as well. We've been kind of queuing for a while now.
Couple of years, I think.
Yes, yeah.
At least 2 years.
yeah. And because like in the beginning it was only traced in OpenTelemetry, we also had our other systems and we queued them as well. And that was in generally pushed JSON data. Certainly Elastic, we were using the Elastic
back when we were using the beats on the Elastic stack. And that was pushing JSON format data.
Yeah, and that's a huge amount of data. OpenTelemetry luckily is standardized on natively a binary standard, and actually now that we're completely on OpenTelemetry, right? Yeah. So we reduced our traffic times 10. Just because we moving
CLS data in gRPC compared to moving even compressed JSON format is much more efficient. And we're actually looking at the recently added Arrow protocol as well. So Apache Arrow for transport for OpenTelemetry that will even like potentially reduce that further. But the reduction in traffic that we saw for the queuing systems, where you pay by the amount of data that you move. So it was important for us, was by a factor of 10 easily between the JSON data from Elasticsearch and the OpenTelemetry data.
Yeah.
So that's another financial incentive to do that kind of thing.
Yeah. We'll still need to see if that impacts a lot because we haven't experimented that.
For Arrow, we haven't looked at yet. We expect a bit of less of a reduction. That's definitely not as drastic. Maybe like a factor, maybe less, another half or something, which is less important for us because it's not that we have over optimization that needs to come before we need to get to that.
Yeah. Voila. And how the metric backends.
Yes.
It's back to you.
Okay. So we talked about a lot about metrics and about how to format them and the cardinality and everything, but we do want to talk a bit about where you send them actually. So metrics usually go to something called a time. Metrics are time series, so they're effectively a metric, and then you have a timestamp, and then the entirety of a timestamp give you a time series. So they're indexed on time primarily, but also sometimes other things like attributes, like we saw. And they are stored in a very large amount. Like the amount of metric that even a simple system can generate is actually baffling. They are stored in a system that we call TSDB, which are our time series database. And if you think about it, almost any system can be a TSDB. You can just create a table in SQL and just have a time column, and then have like a label column, and then, or actually attributes, and then have a metric column, and then suddenly you have a time series database. But the thing is that time series data have some properties that allows us to optimize the system. So usually solutions have particular ways of dealing with them, which are not necessarily compatible with all data, but that helps a lot for this particular kind of data and makes them more efficient. So the specifics are usually write-only. So we never modify those things. We just write them once, and then when we delete them in chunks. So there's no arbitrary deletes. The data is very uniform, so it compresses usually quite well, even beyond the generic compression algorithm like Z standard, for example, or SDMA that you can use. Those are generic. There is even more advanced, like delta encoding compression that you can use on metrics that can save you even more on storage. There is something called downsampling that you don't usually do with normal data, but you can do on metric. So after a while, you can decide to drop some of the precision and then reaggregate the data. Not necessarily supported by all backends. And then there's relatively few indices, right? Like it's not like a DB where you can have indices on everything. Here there is only one specific thing, like the time, and then potentially the attributes, where you're going to have to have indices on. And the query capability is quite limited, right? Like you do selects and then a couple of aggregations, maybe sometimes subqueries, but not even necessarily. Not most systems just support just straightforward querying. I put a couple of self-hosted solutions here. I guess you can see if you, if you see your own. What differentiates them mostly, here I put only two things, but there's sometimes more differences. But mostly what differentiates them is the query language, right? Like Elasticsearch, for example, has a query language called Lucene, Apache Lucene, and they also have an overlay called KQL for Keep and Query Language, and they have a third one, I think, which is called ES something. They started to introduce. Prometheus, and actually most systems nowadays have a tendency to use something called PromQL, sometimes with extension or differences a bit. And then there's a system that uses SQL, like timescale.DB, which allows you to leverage the full power of SQL, although there might be performance impact if you just go outside of the optimized path. And then InfluxDB, for example, used to use something which was kind of like SQL, but homemade. And they moved for the version 3 to something called Flux, which is more like a pipe language. So here you can see that actually 3 of those backends are standardizing on PromQL or a flavor of PromQL. On the right, I put some of the clustering ability, because not all projects allows you to scale horizontally. Some of them actually don't, like Prometheus. They just tell you that, hey, just version 1 instance per team, and that should be enough vertically to scale on that. Some comparison between the two approaches, especially for analytical formats. So we talked a bit about logs before, and Alex is going to dive a bit more into what we mean when we talk about log events and structured logs, but you can actually do metrics in logs. And PromQL and PromQL backends are actually very, very geared towards metrics. They're very, very efficient to deal with that, but they cannot really handle complex data types. Like it's either it's always the timestamp, the attributes, and then one float value that is the actual metric. And the attributes cannot be super big, like they cannot be a blob. They have to be something that is more like a short string. And so for PromQL, it's going to be super efficient for metric. One caveat, though, is that most of the backend will require in-order data, which was actually an issue for us. Because we used to use Elastic for metrics, and we still use it for the most part. And Elastic doesn't have that kind of issue. You can just write data in any order, and it will just figure it out. But for most PromQL backend, because they operate in chunks and they optimize, that means that they can only accept data in order, and they will actually refuse data if you send them something that is a bit messed up in terms of timestamp. But they're very good for metrics and histograms. And on the other side, the SQL and the Lucene backends, and to some extent even Flux, are good for analytical queries. Like you can actually craft longer queries with a bit more subtlety. And they can handle custom format. That means that you can technically send your structured logs to those backends and then get the metrics out of it, and then potentially drill down on the specific events, because you're just re-aggregating on raw data instead of treating the attribute with aggregated data like we have in metrics only. Be careful, though, because with arbitrary formats comes possible schema issues. You can have collisions. JSON don't have types, which cause quite a bit of issues at times. People have a tendency to use a field for something, and then maybe another team will use the same thing for something else. So actually, when you start to do that, data governance, which is actually one of the core things of Collibra, becomes very, very, very much needed. Otherwise, you're going to have collisions, and then the backends are going to refuse some of the documents. But very, very good for log events.
So before diving into this, I want to actually also add that our focus when we actually build our new backend systems, we chose Elastic because you can throw anything at that. The downside is, of course, you actually already have metrics that are aggregated. You put them in documents. That's very efficient. It goes very fast. Although sometimes we have ECAPs, but in general it could handle it. Compared to if you would have like one single Prometheus instance, it would die immediately. But the downside is user experience, like having our all development teams actually learn Lucene. It's not easy and trivial, certainly, because you're looking at aggregates. You need to know the tricks. Max knows all the tricks, but certainly, yes. But not each team, of course. Every time you have like a new team and we need to onboard, and it's like, what is this Lucene? I can't Google this. PromQL, actually, if you probably by now all the AI things that are there, give me a query about this, they'll spew out PromQL. So PromQL is really getting a standard, or is actually the de facto standard for querying metrics. Is actually pretty good. it has a low bar of entry. So that's what we're actually looking to actually go to a Prometheus, but not like a single own self-hosted Prometheus, but like the Google managed Prometheus. Why? Because it's not actually a Prometheus. Yes, the core, the top core is actually Prometheus, so you actually control all the PromQL to it, but it actually uses the Google Magic backends, the Monarch, that can scale like a lot. So actually, not only for making our life easier, but making sure that actually the developer experience is way better to create dashboards.
Most of the open source tools will ship with pre-made dashboard that are actually made for Prometheus backend. So if you don't have a Prometheus backend, you have the kind of curse or the chance to actually go through all of those dashboards and then redo them again for your own use, which is not necessarily a thing you want to do. And I mean, even for Google, they put together initially the Prometheus layer on top of Monarch, but they actually recently dropped, say that they will discontinue their internal query language for in favor of Prometheus. So Prometheus is not perfect, but it's definitely something that right now is the first chop for most of the industry. Very quickly, we talked about the shortcoming of Lucene, or using Lucene instead of PromQL. Another shortcoming that we had is with Grafana for frontend. Lucene plus Grafana, the plugin that we have, only allow us to do one aggregation, which when dealing with counters cause some issues, especially if you have multiple instances of the same service, because then you need to do one difference on the counter, aggregate it per service, and then kind of re-aggregate that on top of that to kind of sum everything together, sum all of the deltas together, and it's simply impossible to do that. We find some workaround sometime by using bucket script and Grafana internal transformations, but it's not super easy to do. So PromQL is much more efficient as doing those kind of like slice and dice with the data, and Lucene has some of the capability that are nice, but it kind of sucks as this particular thing. And then the other one is Alex talked previously about counter reset and what happens when your application restarts and you have a counter, the counter goes to 0. If you have, if you're doing a difference on those counters, then potentially that's going to cause a super big spike on your dashboard if your backend is not properly geared to correctly handle that and kind of like remove that value here. And Elasticsearch has some support for that, but it's not great.
So before taking a break, like one important thing, we already talked about some things to dropping data. Costs, certainly when you're a company at scale, cost of your telemetry actually becomes an issue, and like
cost management.
yes, the management will hook in. Why is this costing so much? So it's certainly like you need to be very everything has a cost, and it actually has a substantial amount of costs. So actually, the team is almost always looking to see how can we reduce the data, because like, okay, all those auto instrumentation that you have, they are producing a lot of data. But what is useful? So there are actually three kind of techniques. You already hinted on a few of them, and that's actually re-aggregating. So two kind of re-aggregating that are popular is spatial, and that's like very tailored towards the cardinalities, lowering cardinality.
You fold dimensions into each other.
Yeah, so actually a straightforward example is when you have like on Kubernetes, you have your application, it has 5 replicas. So each of those have like a unique instance ID, but for some of your metrics, is it important that you know it per instance? Maybe not. So you actually can drop one label or one attribute, and then you actually have still the amount of data that you want. So that's called spatial reaggregation. The other one is temporal reaggregation, and that is meant over time. So certainly in the beginning, you actually want to have like high precision. So the last week, you want to have like every maybe 30 seconds, or some even every 10 seconds. But that data, over time, actually becomes less valuable. Certainly after a week, you don't want to know that high-frequency data. You actually want to see what is your trend. And then maybe you only go to once per hour. And then like after once a week or once a month after years and years of data. You would think that every backend actually supports this. I was actually first thinking like Prometheus, does do this automatically. It actually doesn't. Yeah. So if your backend actually supports this is nice. That's also why we are actually looking at that managed Prometheus. Yeah. It's like
Monarch supports it behind the scene. On Prometheus, if you want to do that, you can in a very clunky way. You have to kind of like re-scrap your data by just like doing queries against your existing data set and then re-recording a new series, which means that you have to define those things for every metric that you have effectively. So maybe if you have a small configuration, that's possible, but otherwise your configuration is going to go completely blow up if you have hundreds or even thousands of metrics.
So, and of course, dropping data, that's the easy one. Actually, if you look at how much data we drop, it's substantial.
I think 70%.
70%. So certainly, if you like, we have a mesh, and each or each Envoy proxy produces an enormous amount of data, and we'll just drop them because we're not using them. One downside is, yes, we know the amount of data that we do. We actually should know actually each and every metric that we're dropping, because probably there are some interesting ones that we're dropping, but like.
It's always easy to rename them. Like
yes,
it's always easy to kind of like, if you drop something, it's usually not too difficult to kind of like take it back again. And certainly from an infrastructure perspective, it's easier to do that rather than to go ask the developers to change the application for that. So it's always better to have an application that is maybe a bit too verbose, but then drop that in your side. To the caveat that reaggregating does have a CPU and memory cost. So the more reaggregation that you're performing on the backend, then the more CPU you're going to burn storing those metrics and then doing those aggregations before sending them. On the temporal aggregation, one interesting thing that we did from the start is that you can have variable level of sampling depending on the metrics that you have. It takes, again, a bit of work because you need to look at your metrics and then kind of like do regex selections based on what you want to keep, but it can be a good cost driver for some metrics that you don't necessarily need to grab every 15 seconds. You can grab them every hour if they don't change that much, and that will save you a lot of money on the back end.
All right, I think we're going to take a break. We haven't gone through all the signals, so we'll take a few of them after the break. I propose that we take kind of a 20-minute break and be back at 11:20, and then we can continue. I don't know if it's practical to do questions now. I don't think so. I think people want to have a break. But if you want to have questions, we're here. So
you're not giving a break, Alex?
Huh?
Not giving a break?
No, I don't know.
No breakfast.
No break. So thanks, and see you in 20 minutes. Okay. Welcome back. I'm glad you came back. So we'll have to move faster because we have way more content than we expected. So we still keep on diving into the signals because this is kind of the most important block. We're going to go faster over an OpenTelemetry, where we're normally at a bigger block. But again, this afternoon there's a workshop. If you're really into OpenTelemetry, you will get like practical examples. Go there. So the next signal, logs. So let's be honest, the oldest trick in the book. It probably kind of existed as long as the first computer was there. You remember your first program, print, console print, hello world. That's your first log statement. The nice, well, actually the downside is that, like, because it's your first thing, you keep on doing this. and it's not always the best thing to do. Still, it's sort of worth talking about logs, and then we'll see how to get less logs and get like less more interesting things and move them to the other systems. So, like your hello world, it's like laying around breadcrumbs all over your application.
Next slide, Alex.
Oh yes, again, I'm doing the same again. We have 2 slides here. So the manual breadcrumbs. Of course, errors you are interested in. You output all your errors in your logs. And you also see like a lot of patterns, like Max already said that like in the previous ones, people are starting to add durations and counters in your log statements. Kind of the first thing of, I want to have like raw data, let's capture them. And of course, logs are being used for doing those things. Luckily, we have by now log frameworks. So instead of doing the console out, although people are still doing that, even I do that in my example programs, but like luckily I have very mature log frameworks right now that guide you a bit into more structure. So in Java, you have, of course, Java utility logging, but I see way more usage of the 2 other frameworks is log4j, and SLF4j in combination with logback. At Collibra, we use the latter. What gives them power? It's actually you give a very simple API to all the developers, a bit more powerful, of course, than like system out, where you actually say, okay, this log, that's the information I have, and then your log framework does like lots of interesting things with that. So 2 important blocks there are appenders and formatters. And actually, the appenders is how do you get all your log statements out of your application. So it could be console out, it could be files, and it really depends on the technology that you use and the agents that you use to scrape or capture your system. So in your application, you could make generic calls for your logging system and then configure your appender. It's like, I'm using this system and I'm using this appender. In combination with that, you have formatters. It's like, of course, you want to actually have sometimes nice, pretty things when you're debugging, like you, as we saw, or you know, JSON is not the most friendly log format to look at. You have console outputted with nice colors that actually show those things. But if you run in production, you don't care about those colors or nicely formatted things. Machines need to consume those things. So you actually want to run like a JSON appender and JSON formatter actually in your production systems. Those frameworks or those APIs actually are so mature though and so long-lived that even OpenTelemetry, that is a new system, when they were covering more and more of the signals, they said like, logs, we are not going to create a specific API for this. We're just going to adapt what exists right now, and we're actually going to just hook into those systems. So they actually write their own appenders. It's like you just keep on using what you have. We'll provide you with an appender, and you automatically have like OpenTelemetry logs. A thing that those frameworks actually introduced is log levels. A mistake that we see a lot is actually people don't care about those things, but you should. Because logs, like everything in telemetry, it costs money. And too much information also causes confusion. So by default, everything what you log is at info. And certainly those breadcrumbs that you put everywhere, actually, the first thing you think is they should actually be in debug, but like the default is the info. So we find lots of log statements just as info level. Ideally, you are actually only interested in more the warnings, error, and fatal. So in production, ideally, you should be able to actually only run with warn, error, and fatal. But that's not the case, and actually push everything to development. We're going to look at events a bit, so we're going back to introducing back info level for events, but that's a bit later. Another concept on logging is actually adding concept. Certainly in an application where you have different things, let's say like a thread ID. You don't want to manually introduce a thread ID with every log line you create. You actually want to have a log line. This is happening now. On what is a thread ID or what is the session ID and all those things. You don't want to manually add that with each and every log line, because before you know it, like log statements like that, and before you know it, you forget it. That's why those log frameworks introduce contexts. You have kind of two different types. Not all frameworks support all of them, but one is like the mapped diagnostic context, the mostly used. Is you put those kind of variables. The current session ID is this value. You run your log statement, different statements. It will all have that session ID appended towards their system. Don't forget to clear that context, though, because it's an easy thing to do, to forget. That's why, luckily, you have those frameworks sometimes have those things handled for you, but you have your own variables. Make sure you clear them. The nested one, you see less used because it's kind of just keywords. You pop and push and pop stuff on there. So collecting, so already kind of covered that the appenders actually is, you actually choose your appenders on the systems that you have. Most patterns that you see is standard in and standard out as output, certainly now in Kubernetes, because that's how it works. I assume most of people by now actually use Dockerized systems or containerized systems, and then you just put everything in standard out. The container runtime actually collects them, and actually in a Kubernetes cluster writes them to disk. And then on each and every of those nodes, you have an agent that collects those file systems. So it's indirectly to files. It's good because it's buffering those systems on a node. So if there's kind of a downtime on your agent, they can catch up. If you're running on a VM in generally, a lot of things that you see is like those files are stored on disk directly from the application. So that's certainly one of the things that's important if you use a framework. But here, this was a horror. When I started Collibra, I said, what is this? So we're using Datadog for our logs. And we started with non-structured. We were not at that maturity level in the beginning. So what you end up, if you don't work with kind of structured systems that don't output JSON, you actually would have lines and lines and lines and lines of configuration issues with regexes in. So you actually, a developer is interested in those durations or something, or the data in those log lines, they actually create a specific a configuration into the parser to say, extract my duration and make a metric out of that. That's kind of horror. So start with going to structured logs. So the structured logs actually introduce more data. Yes, you will have those more human-readable ones, but let's be honest, the thing that works best is actually just code JSON. It makes it way easier. You still have, certainly in log systems specifically, you still will have lines, but it will be way easier to configure. Yep.
Thank you. So one of the other challenges that we have, especially at Collibra, is ownership, right? Because we have a lot of people working on the product team. I haven't counted, but I think we're well over 300 developers. And the teams responsible for the observability systems is much more than that, meaning that we cannot chase them all the time. Otherwise, that's all we do. So one of the things that we had challenges with was seeking out who is responsible for things, because we have terabytes of log, actually hundreds of terabytes per log per month, and initially there was no accountability and visibility, or it was very difficult. Like every time you had an issue, you had to hunt the right team and like take view. I mean, the best that you can have is the Java logger, and just like you take the Java logger, you try to look up which code is actually producing that, and then from the code you can derive which team is actually responsible for that line. This was very difficult, and it's still very difficult, but it's better. It's a bit better. Alex can talk a bit about C4 maybe.
So within architecture, we actually standardize on C4. The people that regularly come to DevX probably already saw Sam Brown presenting here. Last year he did a workshop and he regularly has talks here. And talking about the C4 model, it's kind of a simple model to use and start using with, where you have like 3 levels of detail, starting with a system, then a container, and not to be confused with a Docker container, and then components. In our telemetry system, we use the top layers. Like system is it's like we compose our SaaS platform with the big blocks. It's what is lineage? Okay, lineage is a system. What is catalog? Catalog is a system. And then within a system, within that system, we see what containers, and it's logical containers that you have within, and we start logging that. In generally, it sometimes maps, certainly with the microservices, one-to-one with the container, a real Docker container. Is one container, but we also have a monolith running, and that is actually a module within the monolith that is actually a container. And we tie it like that. So that introducing that already helped. That it looks so obvious, right? You as a team, it's like a simple thing to do as a team. You just add, certainly in a container, you add two attributes, and you're done with it. It was a bit more harder to do in a monolith, but it helps so much. It's like such a small thing to do.
So this helped quite a bit for the teams to be able to kind of like just look at their own logs and not necessarily have to piece together from the entire haystack where are the needles that they care about. Now, the other interesting thing that we encountered in production is the payload limits. You don't necessarily think about it, but logs are effectively one long string for every line in the log file. Or if you just do them without necessarily writing to a log file, you need to send something to the backend that is going to be a log object. And what we saw in the wild was things that were truly baffling. We had literally people on the development team, maybe not knowingly, but we ended up with log lines that were literally more than 2 megabytes long. So this, like, the entire line wouldn't even fit on a floppy disk, right? Like it's very weird, but it happens actually quite often. And when that happens, usually it's because the developers are trying to get some information out of the system. Like they want to get a query, they want to get some kind of like view definition or something that they generate, or even like a stack trace, like we alluded before. The stack traces are actually pretty big sometimes, and they might not even fit in the logs. So those things mean that it's difficult to handle that on the back end, because especially if you have structured logs, then you cannot truncate. Like you're gonna if you just truncate it, you're gonna end up with a truncated JSON, which is not a valid object. So what you want to do is to actually talk to developers upfront and put some limit on the logging side, on the logger itself. So the appender that Alex was talking about. Put some limits in the configuration. Maybe have a profile that is completely limited that they can run in development, but have something in production that actually limits the output. And be upfront with them that those things are limited and they cannot expect to just take an entire piece of memory and just shovel it into the logs, because it doesn't work that way. And then one thing we're looking into, but we don't have a definitive answer for that yet, is to have a separate system to put artifacts that developers want to get out from production, something based on object storage, where they could just push something like a view or a bit of memory or like a dump something in a controlled way that would be referenced from the log, but not part of the log stream itself. Traces. Yeah, sorry. I went to
no
one
problem.
more.
Again, I'm going to do it again, but let's give the developers some credits though. They're used to working on their own machine. They're actually presented in generally with log lines. And like a stack trace for them, if they have a stack trace on their own device, it like shows up nicely. The thing is, like in production, at JSON longs, and everything needs to fit in a line. So everything is kind of up, flipped. And that's why this pops up.
One interesting thing that we did, I don't know if we can talk about it, I think, is that we are pushing developers to actually, even on the laptop, push data to all production telemetry systems in separate tenants. And that allows them effectively to get from the laptop the same kind of telemetry that they get from production, which allows them to evaluate how does it look like. Because some things sometimes just like fits on the laptop and they don't think about it. And then they put the software in production and then realize that actually the stack trace that they have locally, which is completely fine locally, simply like doesn't work on production because it's way too big.
Yeah, it's certainly worth to do it to actually present developers with the same backends as we use in production. So they actually have the same experience. Now, this is kind of my favorite kind of signal. It's traces. Historically wise, it's one of the newest one. And I actually want to push more and more of those breadcrumbs that you have in those log statements to traces. OpenTelemetry by now is pretty mature. That's kind of an easy thing to do. So I always call traces like logs plus plus because on first sight it looks a lot like a log line, but the thing is it has a parent. So you have like say let's just still consider it a log line, but like what happened before. So the biggest differentiator between a log line, there are more, but the biggest one is that it has a parent, and that's the main differentiator. So it has an ID and it has a parent. So an ID is kind of a pointer, so you can point back to it. So then you can create those kind of graphs. It's like, hey, an HTTP call came in. This is the next thing that happens. I actually call this function. So and that function knows where it comes from. So it produces a span. That's what it's called within a trace. That blue box is a span. So it knows where it comes from. The nice thing about traces is that it can be distributed. So there are now technologies, and actually that's why it gets more popular, is that you have ways to actually link a call that being made. And okay, this came from this system, this came from this system. And for us, we're using a service mesh. That means that we have way more proxies than we would like to, but that means that calls from outside comes to a load balancer that now gets a trace that goes to another proxy, and then it goes to the application. That application does a call, it goes to the proxy, then back to a proxy, then to the application. Within traces, those systems are now as mature that they actually understand those things. And we're going to dive a bit deeper of how that works. So how does that distributed thing work? It's actually by context propagation. And so a trace is a unique number, a trace ID. So that's the biggest part. It is just a random number that has been generated. If there's no trace going on, then it just generates a random number. And also, it gives itself an ID for, like, this is the first span. That is not something kind of a structure that represents a trace. A trace is actually a combination of all the spans. All those blue boxes that you saw represent a trace. They all have the same number, but they all have a unique span ID. So how does that work when you jump towards another system? So say this is the trace ID, and the span with that span ID is going on, and you do a call to another system. You add actually yourself, your trace ID and span ID towards your other system. Your other system just picks that up, and that's why we don't call it a span ID, but a parent ID. It gets this in the header. It's just like a normal header that's called trace parent. And actually say, okay, we're already having a trace going on. So I'm actually going to set this as my parent, and I'm going to start a new number. From then, so I have like this trace ID, and then 00009 as the span ID, but my parent is this big number. And that's how actually it's pretty simple. It's just like one header, and that does all the magic. So let's go a bit deeper into a span. So compared to a log, where a log is actually just a message, a span normally has a name. And that name has way more meaning than in a log, so it's get a bit more structure. So in OpenTelemetry, you have semantic conventions that this is how a name of an HTTP call should look like. It starts with get and a path, or post with a path, or something like that. And that's the beginning, that's the name. So you actually can say, okay, this looks like a get, and then in combination with the attributes, we'll make up the complete one. So already talked about kind of on the context, where the trace ID actually represents like this will be unique across all the spans, and that's how everything is tied together. And the span ID you really can consider as a pointer, where the parent ID can point to. A flag, an interesting thing about traces compared to logs. Logs in generally are always consumed completely. You don't filter on that. You actually put them all in a system. In traces, because it's so large, you have so much data. Generally, you can see something when you, at the time where you normally had one log line and you have auto instrumentation, at that time there could be a way more spans. So you have way more data, so you need to sample the amount of data. We do sample pretty aggressively, but yeah, it's to save kind of save costs. So in production we sample way more than in development. It also has a beginning and an end, and that's also an important differentiator from a log. A log just happens now, while a span actually has a duration. Very important, and it makes up those lines. And in your backends, you can see when does this one start and this, and how is the relation between those things. And it's a very powerful concept. You have also, while you have log levels in logs, in spans is pretty simple. So you have it's okay or it's an error. And there we can actually base some of our sampling decisions on off. So you could say, I'm going to throw a lot of just things that went right, just out of the door, but the ones with errors, I'm actually going to keep to do deep analysis on. An important concept is attributes. Just like everything in OpenTelemetry, everything is attributes. There's important information. In combination with a name, it gives like a lot of detail. So where did it come from, and what is the duration, even there, those things are added. Pretty unique to OpenTelemetry is that you had that parent-child relation existed for a while. You do see even more async operations, where that kind of you have this call, it goes from system A to B, and then B actually fires up something on a queue, and that will be processed later on. So, and here you have actually linking. So you don't want to have like a trace that could say that your job schedule only runs every hour, and you actually set something on a queue, like 1 hour plus 1 minute. Okay, put something in the queue, and only 59 minutes later on it gets picked up. You don't want to have a trace of that HTTP call for an hour. It didn't take an hour. It actually directly went back in like a second, but it set something on a queue. So here you can use trace linking. It's like, okay, we set something in the queue. This is the parent. You start kind of a new trace and you link it back. It's pretty easy to do, and we have actually this in our demo. Did I do this? Sorry. So yes, we're going to skip this. No, we're not going to skip this. So how do you do sampling? Sampling. So head sampling is a pretty basic way of sampling. It's like you just take 5% or 1% or 0.5% of your data, and the rest you drop. How do you do this? It's pretty simple. You have a trace ID. You say make a hash of this, and you say we're only gonna take that amount of traces based on the trace ID, and the other one is tail-based sampling, and is that based on that error that is on there. The only downside of a tail-based sampling, though, is that your backend or pipeline in between needs to collect all the traces, all the spans of that trace, and to see if there's an error in there. So tail-based sampling, we're not doing that at Collibra. We're just doing head-based sampling, because our backend actually doesn't support that, and we don't want to build our own pipelines to actually do tail-based sampling.
If you have a lot of traces, tail-based sampling takes a gigantic amount of resources, because you actually need to hold the entire trace in memory. If you have short calls, then that's fine. You need to hold 30 seconds maybe, or maybe 1 minute of your data in memory. But as your calls go longer, then that's going to mean that you're going to need to hold more and more. And the more data you have, the more memory you burn. So to some extent, for some small systems, it can work very well. At our scale, it would literally take terabytes of memory simply to try to do that.
One thing about the good news for tracing, and certainly Java, I know in DevBox there are a lot of Java developers focused on Java, is that OpenTelemetry tracing is super mature. It has automatic instrumentation, and I certainly would advise, if you just try out, start with auto instrumentation, and then the next step is manual instrumentation. The automatic instrumentation should just be a starter, but it really helps you. You don't have to consider doing that trace propagation between services. How does that work? You actually inject an agent in your JVM, and it actually looks for patterns. An HTTP call of a client, it actually detects that, and it writes the code around that in bytecode. It does the same for a lot of popular frameworks. Everything in Spring is supported. Whatever, even like schedulers and so on, it actually works out of the box. You really see traces on there. But that's like generally the outbound and inbound calls, your schedulers and so on, but it doesn't capture a business logic. So it's a good starter, but do manual instrumentation as well, because you actually, remember, right, you leave breadcrumbs into your application, and then actually it's more to capture business logic. Stop doing that. Actually start doing manual instrumentation, and just start doing that in spans. It is way more valuable, and to debug things kind of in production where you actually can follow that thing. Remember a stack trace, right? It has like lots of value information. It's not readable. It's like logs. How do you kind of combine those things? It's way easier to do that in traces. So it's well worth the investment for troubleshooting. Voila. So eventing. This is what, in OpenTelemetry, one of the newest ones. It's only a few months that it's kind of finalized. It is actually totally, it didn't introduce anything new on the protocol, but it's totally based on semantic conventions. So saying, just like the traces, are based on semantic conventions. This is a name, these are attributes. Events within OpenTelemetry is like, okay, we have an attribute that is event name. That's the name. And we expect those attributes to be present for that kind of event. And that's the meaning of that. So it is very comparable. You know, people are pushing for API first. It's very comparable. So an event should be actually kind of thought about how should this look like. OpenTelemetry has tooling for those things to even generate code. We haven't used those things. We started with eventing on our own system, but we will move to this.
The eventing, even before the spec was here, we started to do eventing just based on structured logs.
Yeah.
But the specs makes it a bit more formal, because if you just tell people to do structured logs, you are going to lack the well-structured and the semantic convention part of it, which makes the data set a bit difficult to deal with.
Yeah, and that's where the typing comes in. Before you know it, people are actually trembling on each other's toes on the attributes. Like, okay, I have my specific workflow, it has that ID, and the duration is that. And somebody decided to put a string on there, and another team is like, duration is like, it feels like a logical thing, but like put a number in there, and then if we route that to a specific system, you get clashes like that. That's why it's actually very important to do governance on those systems. So don't do events without governance. It's better to start logging and then see what could be useful, and then start doing events, because it shot ourselves kind of in the foot. We find our eventing system based on JSON logs pretty successful because it's used a lot. It actually involves the business. It's actually, the business is also very interested in those things, because that's where you can say, this is an important business event. We're going to make an event out of this. We're routing this to different kind of more analytical backends, actually to Elastic, but also to BigQuery, and then routed to another department where it's like, now it's your data. Do things with those things. So events are way more data points that have way more business values. And it actually, instead of making it just an operational thing, your signals, it actually could help stakeholders within management to say, here, we're doing useful things. We're producing our business events for this. Events characteristics, it's raw data. So think what you did before with those durations in your log events, just make them more structured. Think about this is event name, this is an attribute. We're using this attribute across events. It should be all the same. That's about the governance. Cardinality is kind of less of an issue because it's raw data. It's all stored as a whole, as raw data. And those systems like Snowflake and BigQuery and Elastic, they can handle that. Voilà. So this is, for me, events and tracing combined are actually my favorite signals. We have some leftovers.
There's one last what you're going to talk, which is not something that you reach out usually unless you are doing something which is very performance critical, and that's profiling. Profiling signals are effectively a combination of traces. So if you think about it, this is an example of a flame graph from profiling tool. And this is a CPU profile, but you can do it as well with memory by looking at the allocation. This is the amount of CPU that is used by every function across time. And profiles are done across, they're kind of like an aggregate of traces. So if you take all of the traces over like 10 seconds, and then you assemble them together, then you get effectively a sense, if you get every single one of them, you get a sense of what the system is actually doing at that point. Like if you're burning 100% CPU, then those traces are going to be the share of CPU, the CPU share that the functions are effectively using. And so where traces give you the journey of a single request and the latency associated with that, it doesn't give you the resource usage. The profile will actually tell you at a certain point in time what your system is doing. And that's going to be very, very valuable if you have a system that is consuming a lot of resources, and then you want to know where that resources are spent. Profiles are kind of the way to go. One caveat though, they're not yet in OpenTelemetry, although there is a big push to get them in. Elastic donated their eBPF profiler to the OpenTelemetry project, and they're kind of like working on the specification. But right now, they are not really in the spec itself. But you can still get some vendors that will give you a profiler by itself, usually with their proprietary APM solution. And that can be useful if you have those particular issues with resource usage.
So closing thoughts on the signals, we've covered most of them, and actually this is what we actually want you to actually take with you. So let's think about tracing for your breadcrumbs. Stop doing those in log statements. Operational teams.
Operation start. Operation is in process. Operation ends.
Yes. So that's not useful as a log line itself. And certainly if you have lots of concurrent systems, it's very hard to do that. You have to start filtering on logs, while in traces they are already combined out of the box, and it's very easy. Just dive into this. It's time well spent. And if you really want to have those things in logs, there exist converters from traces to logs, but don't do that.
One of the things that we saw in the wild is people writing spans and potentially effectively writing like a structured log for every span. And those can be either a span or log, depending on how you configure it. It's still interesting to have some logs though, because you do need to find those trace IDs. Like you cannot really search on spans usually. Although some buckets allow it. Usually it's a lot of data, so it's not necessarily indexed. So having some logs are interesting, like, I don't know, the request log itself, like just the summary of the request. And then that log can have a trace ID that gives you the trace with the complete details. But you don't need to, if you do that, you don't need to go through every service with like, hey, processing starts, processing stops, operation took that many seconds, etc., etc.
Yeah. So, and then the next thing is start thinking about events, also things that you probably already did in logs. Start looking at or following what happens on the events. But even if you don't do the OpenTelemetry events yet, thinking about those things is a very good starter and could help the business. And then well, look at metrics as well. But like I think like look first at the three other ones. Look at metrics for some very important things like a queue, and certainly things that you actually want to alert on. Because in generally, events and traces are actually used later on. Like events, you can do kind of aggregation in pipelines on those events, but it comes with a delay. While you're producing in your application those metrics, they are actually exposed directly. There are still some scraping or push delays there, but it won't take like, instead of like 2 minutes, it will have like 1 minute delay. And if you have alerting or even kind of scale out events that you want to act on those metrics, those could be really interesting as metrics. But those are actually already on the third place. And then, yes, of course, I don't want to say stop doing completely logs. There is still some use for it. So, but it should be actually at the bottom and not on the first line. So
we actually get to OpenTelemetry.
Yeah.
After all that time.
Yeah, we have 20 minutes. So we'll go very, very fast on OpenTelemetry.
They can do workshop if they want to. Or they can go with the spec.
So OpenTelemetry. I want to talk about the community though, because OpenTelemetry though it's pretty unique. I don't think I saw this in open source. Maybe it exists, but I'm not aware of this. It's actually a combination of two projects. So Open Sensors and Open Tracing, they actually said, we're doing the same thing. Let's just bang our heads together and actually make sure that we have something useful where there's not a lot of confusion. And so they actually at 2019, just before COVID, they actually said like let's combine the two projects and make OpenTelemetry. And I think it's the right decision, because if you look, it is actually well, first of all, a very important fact is that it's an industry backing. So since they combined, a lot of those vendors actually saw like we're all making our own proprietary SDKs, and actually those SDKs don't bring a lot of value. There's so many things to auto-instrument on how to do those things. It doesn't bring value. We actually want to specialize and focus on our backends. We want to make sure that our backends are the best, so they can still compete on that level on the backends. And then actually combine forces with each other is like, okay, how do we instrument? How do we let people do the same? It's wonderful to see. I sometimes go to those Zoom meetings, and sometimes there's a fly on the wall or something to discuss, and it's like people from Microsoft, like Splunk, and like they're really competitor in the space, but they're really thinking about how can we make this the best thing to do, and it's very nice to see. It's pretty unique. And it has some success because it's kind of the second largest CNCF project. CNCF is a cloud native foundation where Kubernetes is in. It has lots and lots of projects as well, but it is number 2. Kubernetes is number 1. Okay, fine. it exists longer, so maybe OpenTelemetry will become popular. You never know.
It for sure matured a lot because we were onboarded very early. I think it's been more than 4 years that we've been doing OpenTelemetry, and we saw the specification evolve a lot. I was going to say product. We saw the specification evolve a lot since we started using it, and most of the time when we encountered issue, those were later fixed, either in the specification or we did it ourselves because the code is open. One of the big issues that we had before was that for everything, when you have a vendor, you need to convince the vendor that this is a good idea. You cannot really extend what they have or at great cost in terms of development. But for OpenTelemetry, especially, Alex is going to talk about the collector, we found a lot of the problem that we had to be things that we could fix simply by extending the collector and the specification, leveraging the core, but also adding stuff that we wanted to do for our necessary use cases.
Yeah, the funny thing is that we probably still are using our own Datadog exporter. I don't know if we still do, but I think so.
I think we do, actually.
Yeah, because in the beginning, actually, Datadog is like, okay, like the spec is so new, and we were super early adopters on log, so we can't export to Datadog, so we wrote it ourselves. It's pretty simple to do. Yeah. It's not that it takes like 5 sprints. I think like we did it like in half sprint or a full sprint or something like that, and you have an exporter, so it's pretty simple. And that's a nice thing and something to remember about OpenTelemetry. It's more a spec. So quickly on the OpenTelemetry protocol, this is kind of the backbone of what OpenTelemetry is. One of them, aside from the SDKs. But the protocol is actually one of the most important parts. It's written in protobuf, and it actually helped us a lot. Certainly from an early adapter point of view, we actually never lost data since the protocol evolved. So even some of the names and so changed from those messages, but because it's really based on protobuf, compatibility is actually one of the #1 thing that system is built upon. It was very easy to actually evolve, and actually without downtime we to evolve alongside with the spec. So quickly over one of the signals. So I'm taking here the span example. I will go quickly in there. The thing that we discussed in our signals, you will see here just as messages, the trace ID, span ID, state, parent ID. You will find them all here, even the special things like the attributes. The attributes, that's a nice thing about OpenTelemetry. Across all the signals, it's just the same data type. So once you use them, it's very easy to do because you will recognize the pattern. We're probably some advanced users because we have data flows or Apache Beam pipelines that actually really use the raw data, and because the patterns are so familiar, and also you can generate the code from protobuf to handle the structure. It's very easy to do. I don't think you do that from the beginning, but those patterns come into the collector as well, and so that makes it very easy. I'm going to skip those details here. But what another thing you will see in the spec is that there is a hierarchy. So you have spans, you have logs, you have metrics, but they will always be kind of encapsulated by a scope and a resource. So the scope actually represents the instrumentation in generally. If you make a library, for example, you say, okay, I'm making metrics for this library, I'm making logs for this library, I'm making traces for the libraries. So you actually say, I'm doing this in the scope of this library. You can also use this within your company. It's like, okay, I'm setting the scope, and the scope is a library. So everything that you do within that library, I will have that scope attached. So you can actually, even if you do those traces and logs, you can say, only show me those things from the library. And then the next stage is the resource. And the resource that will come really to infrastructure, although they consider an application itself also a resource. And that's also where the spec of OpenTelemetry is kind of involved, of having a hierarchy of those resources. But now there's only one resource, and that's either the application. Well, it's actually what they actually do. They're flattening things out, right? So the application, this is the process ID. So and that's again where the semantic conventions come in. Semantic conventions actually shows, okay, a process attribute is like process ID. This is the name, this is a service ID, but then that process lives in a container, and then that container ID has, let's go to the example of the container actually. So the container ID has all those attributes, and those container attributes all live on a Kubernetes cluster, and those things are added as well. So a resource object will actually have all those things kind of flattened kind of together.
The cluster, the cloud provider, the region,
yes,
the
even those things, yes.
All of those metadata that you expect to kind of locate your service are going to live as resource attributes.
Yes, yes. So this is what the state where we're in now. It's only one object, no hierarchy, everything flattened down. To be honest, I don't think that's a big problem, because the semantic conventions make sure that they actually don't collide. You do not see what a hierarchy is, but if you know a bit of infrastructure, you actually know how things are glued together.
It also helps because it means that you have a single resource attribute that you can filter on across all of the signals. You can use that for metrics, you can use that for logs, you can use that for traces. Especially if you end up using different systems for the free signals, having a single way to kind of designate things makes things much easier for developers to cross-check and then to manipulate those systems, because otherwise they need to remember every time what kind of filter or kind of tag they need to use. Elastic use fields, other systems use something else. Here you have a single semantic convention, and there's no discussion, even if they want to create something new, about what it should be.
A lot of activity within the spec is now centered around semantic conventions. I have here kind of the areas that those specs are written out and actually getting bigger and bigger and bigger. It shouldn't stop you, though, to actually create your own, because there are a lot of business-specific things that will never fit into the general semantic conventions. The nice things, they are scoped as well. So you saw the container is container dot. We start Colibra dot, and then we have our own semantic conventions, and that will help you again, like correlating between all those signals.
The C4 tags that we're talking about is one of the things that we came up internally because they don't exist in the resources. So we just have a Colibra.C4 container tag that basically can be used across all of the signals, and that will give you a filter on what kind of container, C4 container the application is.
So, skipping quickly to SDK and other things. So the protocol number one, but for me. The second thing is the SDK. And we're in luck again. Java is actually one of the most stable ones. I think Go as well. Well, let's focus. Next slide. Sorry. Yeah,
No, it's just that you have this.
Oh, sorry.
There you go. That's good.
Yeah, sorry. So Java is one of the stablest ones. On the agent one, I already mentioned for the auto instrumentation, it already is on version 2. And because we're living on the JVM, there's so much mature tooling to do bytecode manipulation. It's so easy that actually a lot of value is in there. And really start with the agent. So in our quick demo, I'll start with the agent. It will be a very quick demo. Don't forget about the collector. I think this also contributes to the success of OpenTelemetry is that they had a collector. That collector is actually pretty simple, straightforward pipelining mechanisms. It has receivers, it has processors, and it has exporters. What it actually allows us to do, or actually whoever implement, is like, what are the legacy things that we have, and how can we actually hook them up together? I have here a slide of like, I'm not going to read them all, but like we have even they can't fit on the screen. So we have 95 collectors that are in open source collector contrib repository. The one that is highlighted is written by Collibra, where we use PubSub as kind of a backend system. And so it wasn't there, so we just wrote it and actually contributed it back. You have lots of processors. You even have tail sampling in there, but we probably have two big traces, or then you have to manage those things yourself. And exporters actually the same. Well, it will be less, right? Because they're focusing on getting everything towards OpenTelemetry at the back end, but it doesn't stop you from actually writing your own system. You don't have to tie yourself in as a protocol level to have benefits. You can still have everything on an SDK. You collect everything and then actually transform it to your own backend systems. So pipelines, quickly. Normally, you do that for transformation. For us at Collibra, our pipeline is one of the kind of our cornerstones of our, we'll call it the telemetry backbone. Because before you had all those things glued together, we want to kind of give a bit more structure into that, and that's through our telemetry backbone. So at the top, you have kind of Kubernetes. We have dozens of them. At the bottom, we have still lots of VMs. So we standardized on that. On the VMs, we put like a collector. It's always the same binary, just configured differently. If it's actually meant to kind of collect on a VM, you say it's an agent. At the top in our Kubernetes, our first iteration is like we collect everything on the node level and then send everything to kind of a collector that sends everything to the backend. So you only have to configure everything at the backend on one place. But we're actually moving away from that. But we actually said like, we don't want to actually send everything to the backend because we want to get the business value on there and actually want to do some queuing. So this is kind of the obvious next step, although you don't have queuing, but you only have like, okay, this is our backbone, everything configure and send everything to that. That backbone now sends everything to the backend. I don't think we ever did this intermediate step. We immediately went to everything on, for us, Google PubSub, but it could be anything. It could be an AWS, it could be Kafka, not to be named Kafka. Probably Kafka. I'm sure there is a Kafka in out as well. So put everything there, and it actually enables, only this step enables you to actually own your data. For me, OpenTelemetry is all about owning your data. If you send everything directly to the backend, yes, maybe you own your data, but if you actually want to get business value out of it, you have to extract them back out of those backend systems, and generally that costs money. So why not actually do those things on the raw data? So we actually have those data flows. So Apache Beam or whatever, it could be Spark or Flink or whatever. you actually use the array data and extract business value out of that. We are more and more using, going forward, instead of doing streaming, we're doing more and more batch, because those business value doesn't need to be like on the minute. So a daily extract is actually more cheaper to calculate. So we move. That's kind of our system. We're kind of optimizing now. Now a bit. I think we're at that stage where actually we said like we don't want to have like an intermediate collector on the Kubernetes cluster. It's way easier because we are in control of the configuration anyway to just have like the agents on each and every node to send the data directly to our telemetry backbone. And now the new things that we are moving towards is actually we're going to send directly everything to PubSub. That is a specific reason why we're going to manage Prometheus. Managed Prometheus still needs to have data in order. With that telemetry, with the telemetry backbone, everything going over gRPC, there are a lot of things that you can multiplex and data can get out of order because we optimized for throughput. We had lots and lots of data. This gives us the opportunity back to get like order again. Order on PubSub is like a trade-off. It will have a lower throughput, but we're sure that the throughput will be more than enough. It should be fine, yes. We're big, but we're not that big. Voila, so closing thoughts. OpenTelemetry for me is a future, I'm sure. There's no question about that. If somebody comes, could you look at this proprietary SDK? I'll take it. So just, even if it's a bit harder, it's still a very young process, so it's evolving a lot.
It's moving very quickly.
Yes, it's moving very quickly, and that comes with a cost as well, right?
You need to keep up, like for example, the collector releases every 2 weeks. So I think on our side, we update all of the agents in the fleet at least monthly. We also have a couple of development internally on the collector that we need to update every time they do a change.
Yeah. We build our own collector because we have our own exporter still that we use, and it does our thing. We don't want to update those things. Voila. Another practical.
10 minutes for a demo.
10 minutes for a demo. Luckily, I have some slides that I can say. I can use. Proprietary SDKs, we don't care about the proprietary SDKs. Micrometer is the first step, but if you go, just skip Micrometer. Just go direct.
Project. If you're doing Greenfield, there's a way now to just use this SDK directly.
Yeah, and the reason why I mentioned the agent, the Java OpenTelemetry Java agent recognizes Micrometer, and it will actually transform that and make it OpenTelemetry. The downside is the semantic conventions are actually very tight to the SDK, and Micrometer has some kind of opinions that are not really compatible or kind of conflicting with OpenTelemetry. So if you can, just skip and go directly to OpenTelemetry. Use the agents, and we'll go and look at why. Do manual. There's some manual setup to do. But there are three ways to do it. Use the agent. You can set everything manually, create classes, configure everything locally, push that everything in your code. Don't do that. Use the agent. If you're building native images with Java, there's also now a solution. There is a Spring Boot OpenTelemetry starter that you can just include. I think it has way more limitation than using the Java agent, but I think you can get very far with this one. So if you use, build native images. Let's skip that. Oh no, I had like a lot of slides for the collector. If you do development, use a collector. You spend the effort to have that collector in there, so you can actually send your data to your collector. It's not that hard. You only need to know how the configuration looks like, but it's pretty simple. You have receivers, you have processors and exporters. You configure them, and An important one that you will use locally is debug. So the debug one, it will just textually dump everything, and you can all use them at the same time. So you can send things to a backend at the same time do debug. If you want to switch, just to restart the container, I have it here on my machine. I've built it because we contribute, so we just have it in our system. But it's certainly worth it. That's what I talked. We have like now distributed within our company just a command line that people don't have to think about anything. They start that up, and it actually sends to our backbone, and they can use those things immediately. Voila. Processing, very easy to do. Okay. Gradle configuration. I assume that people know how to put some extra dependencies. And by the way, we have a workshop, so they will go pretty deeply into that. I would show you, we have no log configuration. It's all standard logging. And here we are. An interesting thing to do is to make sure that you, into your configuration, copy your agent, put them into the Docker, because that's not so obvious. So we have a copy command, we put it in our zip folder, and those things we actually build that. Teams just copy paste those things from the original one. Locally, if you want to actually locally, this is the only thing you need to do. So once you have that, you use that copy jar. You just reference -Java agent, reference the jar agent, and it actually has everything by default. The defaults are, of course, in the spec, and the default is everything OTLP out. So you will have directly complaints. If you don't have an OpenTelemetry collector running locally, it complains, I can't send data. And that's where the push thing comes in. So it will complain. You can configure all those things with system variables, environment variables, and so on. But that's why I say start with the collector locally as well, because it will help you out. I'm just going to dive quickly into the code. Let's skip those things. Oh. Let's see. Display settings. Always a challenge doing multi-screen demos. So, mirror built-in display.
Yeah, that's good. You're good.
Okay. All right.
So what Alex prepared is a small demo with a Spring application and then the collector in.
Yeah, so the collector is running here. What you will get here is like the debug information. And make sure not to put JSON logs in there because then it's not readable, because this is just for consuming locally, but all your telemetry signals, you can dive into that. You can use then the processors to actually zoom into what you have. But within the spec, if you're kind of familiar now with the system, you will see a lot of things here in there. So the Java application, you do see it? Yeah. That's all right. Is it big enough?
Big enough in the back? Yeah.
Good. Okay. So I actually have one simple controller, the Vox controller at task. So an important part is that you can use spans. So, well, the initialization happens at the top, right? So you get just a global tracer. We use a global tracer because the Java agent actually converted everything. And here's the instrumentation. So we only have one instrumentation. We don't have libraries. So we say like our instrumentation scope name is our application. And we have this version of the instrumentation. And here I'm going to use a call, an HTTP call from this controller to itself. I don't touch anything. I'm just using the standard HTTP client, and I'm not adding any OpenTelemetry things. You can do that if you don't use an agent. You have to add specific things. Then you say, I need to propagate these things. I have a wrapper for that HTTP client. But because we're using the agent, it actually sees that there's an HTTP client in your build, and it actually will pick this one, and it will actually brew that code in bytecode around this. So spans will be generated, even metrics will be generated. And here I do the requests. It's maybe not the prettiest code. I have an excuse, I'm an architect. So I'll send the data, and I'll send this just to Pong. Let's see. Ping, send. So I will do a few.
And it works.
And it works, yes. Yay. So let's see how to load. You see my ping. While Pong was called, you actually only see here, if you see in the most recent calls, only ping. Why? Because it actually recognized. Let's zoom into one. It actually recognized. So here's the Pong. So because the agent actually instrumented the client, and it of course instrumented itself for inbound calls, it actually said like, okay, I'm going to do the HTTP client, I'll add a trace header, do a REST call over localhost to itself, and it will pick up where it left off. So even while you go over a network, things kind of hook into each other. And this is a very powerful thing. If you use the agent everywhere and you standardize on the defaults on OpenTelemetry, for me it's important to actually focus on the defaults, because otherwise you have cognitive load of like, how do I configure this? You actually don't have to configure it at all. And voila, so it's all kind of glued together. What? This lost?
Expanded.
Yeah, okay. So we actually didn't touch at correlation as well, but like what OpenTelemetry is good at is actually tying all the signals together. It actually is powerful on logs and traces, that it's obvious. It uses that MDC context to adding to each and every line that is in context the trace ID and the span ID. If you send them to a system that actually understands them, even if it's like the logging API and the tracing API here, it actually sees that those things actually, that it recognizes that. So, and it will then interpolate those things. If we go to the logging API as well, so you actually also see that you can go view trace detail here, and you actually jump to that. So you can go from your logs to your traces, and from your traces to your logs. This is very powerful, because if you say logs is kind of very horizontal, and then like here's my trouble point. Okay, this is, and then you go actually vertical for your traces. So you slice that one out. So you can even
do the same for metrics as well.
So for metrics as well. So I'm going to have another point. I'm just going to do the task. What it does, it's actually add something to a task queue. So send. I'm going to do it a few times. So, and then every 10 seconds it picks it up. It will do those things. And let's see. Now the hard part is waiting, because only every minute, so it's collecting those metrics, it's creating internal data structure, and only every minute it will push those things out.
So you can pick one up from these two.
Yeah, let's see, but like, because it's a long talk, it could be. Let's see.
More than 3 hours, I think.
Yeah.
Maybe 10.
Oh man, it's like
right?
this.
If you pick like 3 days, maybe?
No, if you don't have like lots of data, it could be tricky. Let's see. Anyway, while waiting for this, so I'm going to quickly show the code, and then we're going to stop and wait for questions, and then maybe we'll see it popping up in the meantime while we wait. So the task, what it did is like, hey, we're just adding a task to our task. We're putting a random number. That is actually the time we delay. And then in the task manager, we just pick it up. And the important thing is, though, is then as soon, because it's async, you are responsible to propagate that trace parent. And that's why we actually had the trace context as a parent in our task and that number. Because when you then do your work, here you have to add a link. So add a link is like, hey, this is my parent. And then you will see that those things happened. I think we can already go to the trace, and we will see here the big one. So here you see that I clicked a few times. I clicked like 7 times. And here you see the link icon. So if you suspend, so you see that thing that I did here, actually that command came from somewhere else. You can see, and you can click on that, and it just will open up the original one, and it's like, hey, it's the task one. So this is very powerful, also for metrics. And you have exemplars where you actually have like dots, and you can look at the tail latency then, and you click on that, and you see that trace. So I think we're going to wrap up because we're already over time. So any questions? And we will stay here as well. Right? So thank you.
Thank you.
And don't forget the workshop.